Hello, I'm Dr. Megha Bhamare, working as Assistant Professor in KVNI College, Nashik. In last session, we have seen relations, equivalence relation. Now in this session, we will see examples on equivalence relation, the topic equivalence class, and partition of a set. Now, what is equivalence relation? It is a relation on non-empty set A. It is equivalence if and only if it is reflexive, symmetric, and transitive. Reflexive means for every x belongs to A, x is related to x. Symmetric means for xy belongs to A, if x is related to y, then y is related to x. And transitive means for xyz belongs to A, if x is related to y and y is related to z, then x is related to z. Now we see example. Let A is equal to ABC be a set and R1 having elements AA, BB, CC, AC and CA. Then show that R1 is an equivalence relation. Now we find solution. For this, first we show that it is reflexive, symmetric and transitive. For reflexivity, we consider elements ABC belongs to A. In this set R1, AA is present, BB is present, and CC is present. That is, AA, BB, CC belongs to R1 and therefore all elements of set A is related to itself and hence we say that it is reflexive. Now, symmetry. For ABC belongs to A, if we take AC belongs to R1, that is AC is in set R1, then CA also belongs to R1 and therefore relation is symmetric. Transitivity. For ABC belongs to A, if AC belongs to R1 and CA belongs to R1, then AA also belongs to R1. That is, AC is an element of R1, CA is an element of R1, then AA also an element of R1 and hence relation is transitive. That is, given relation is reflexive, symmetric and transitive, therefore it is an equivalence relation. If we take another example, let A be any set consist element ABC and R2 is defined on set A as AA, BB, CC, AB, BC, AC, BA, CB and CA are elements of R2. We have to check the relation is equivalence or not. If we solve this example, then we see that relation is reflexive, symmetric and transitive. Therefore, it is an equivalence relation. Now we take another example. If R be the relation defined on set Z cross Z as AB is related to C, D, if and only if A plus B is equal to C plus D, then show that relation is an equivalence relation. First we check relation is reflexive or not. For all order pairs of A, B belongs to Z cross Z, we see that A plus B is equal to A plus B and hence we can say that AB is related to AB and hence relation is reflexive. Now we check symmetric relation. For any element AB and CD belongs to Z cross Z, if AB is related to CD, then A plus B is equal to C plus D. But here we have to show that CD is related to AB. But we can write A plus B is equal to C plus D as C plus D is equal to A plus B and hence CD is related to AB and therefore relation is symmetric. Next we check transitive relation. For any AB, CD, E, F belongs to Z cross Z. Here we take three elements. First, if AB is related to CD, that is first element is related to second element. Then by our relation A plus B is equal to C plus D. And we take CD is related to EF. Then C plus D is equal to E plus F. Hence, by using equation 1 and 2, we can say that A plus B is equal to E plus F. That is, the element AB is related to EF, and hence the relation R is transitive relation. Given relation is reflexive, symmetric and transitive. Therefore, it is an equivalence relation. Now, we see equivalence class. Let R be an equivalence relation defined on non-empty set A for element x belongs to A. Its equivalence class is the set of elements of A which are related to x. That is, equivalence class of x is the set of elements y as in A such that x is related to y. That is, all elements related to x belongs to that set x. Now we take another example. If set A consists element A, B, C and R is the relation defined on set A as AA, BB, CC, AC and CA. In this relation, we can find equivalence class. Equivalence class of A is equal to A comma C. That is, A is related to A and A is related to C, and therefore in equivalence class of A consist A and C are two elements. Equivalence class of B consists only B because B is related to B, and equivalence class consists A and C because C is related to C and C is related to A, and hence we can say that equivalence class of A is equal to equivalence class of C. Partition of a set. A partition of a non-empty set X is a pairwise disjoint collection of subsets of X whose union is X. That is, a partition of a set is a grouping of its element into non-empty subsets in such a way that every element is included exactly one subset. Now let us consider here P1, P2, P3, P4 and P5 are partitions of some region. Here we see that P1, P2, P3, P4 and P5 having no common region, but intersection is empty, and if we take union of them, that is if we collect all the region, then we will get set X. Let us consider an example, that is set X consists element A, B, C, D, E, F, G, and we take partitions P1, that is AB, P2 consists element C, P3 consists D, P4 consists E, F, G, and P5 consists H and I. Here we see that any two partitions, that is P1 and P2, having no element as a common element. Here P3 and P4, in P3 it is D, in P4 it is E, F, G. That is, intersection of P3 and P4 is equal to phi. That is, any two partitions or intersection of any two partitions is empty set. But if we take union of these five partitions, that is P1, P2, P3, P4 and P5, then we will get set X, and hence we say that set P is a partition of set X. Now see another example. If set A consists elements A, B, C, then find all partitions of A and corresponding equivalence relations on A. Here we find partitions P1, P2, P3 and P4, P5 in such a way that intersection of them is empty set and union of them is set A. That is P1 consists singleton elements ABC, P2 consists ABC, P3 consists AC and B, P4 consists BC and A, P5 consists A, B, C. Here, equivalence relations corresponding to partitions P1, P2, P3, P4 and P5 are respectively R1, R2, R3, R4 and R5. R1 is a singleton set, that is R1 is a set consists element AA, BB, CC. R2 is a set consists AA, BB, CC, AB and BA. R3 consists AA, BB, CC, AC, CA. R4 consists AA, BB, CC, BC, CB and R5 consists AA, BB, CC, AB, BA, AC, CA, BC and CB. Thank you.